Hi, I'm Christoph Saulder, currently a postdoc at the Korea Astronomy and Space Science Institute, and today I will give you an overview of the DESI Peculiar Velocity Survey. Over the course of my talk, I will explain how we select targets for the DESI Peculiar Velocity Survey and how this program will benefit the overall science produced by DESI and contribute to our understanding of the universe. Of course, I'm not doing this project alone. I'm just a small part of an ever-growing group within DESI that works on this project. Just to name a few of my collaborators whose work has been crucial in designing the DESI Peculiar Velocity Survey: Kyle Howlett, Khaled Said, Kylie Douglas, Segev Ben-Ziv, John Lucy, Alex Kim, Anthony Kremen, David Parkinson, John Mustakas, and many others that have contributed and supported the project so far. Peculiar velocities are the proper motions of galaxies relative to the Hubble flow. In order to obtain peculiar velocities of galaxies, one needs to compare spectroscopically measured redshifts to a redshift-independent distance indicator. While standard candles such as Cepheids and supernova type 1a are very precise, they have also some notable disadvantages when it comes to peculiar velocity surveys. Cepheids can only be measured using a considerable effort and within a limited range, as sufficient angular resolution is required to detect them. Supernova type 1a are too rare for a consistent and dense sampling within the local universe. Despite their considerable intrinsic scatter of about 20%, galaxy scaling relations such as the fundamental plane and the Tully-Fisher relation have the advantage that it can be applied to a very large number of galaxies within the local universe, which balances out the disadvantage.
The fundamental plane is an empirical relation for early type galaxies that can provide the physical size of a galaxy given two distance-independent quantities, namely its central velocity dispersion and surface brightness. By comparing the predicted size to the observed size, one is able to derive redshift-independent distances using simple trigonometry. While we can obtain sizes and surface brightnesses from the DESI Legacy Imaging Survey, we need additional observations to obtain high-quality spectra to reliably measure the velocity dispersions of these galaxies. The Tully-Fisher relation is an empirical relation for late-type galaxies that can predict a galaxy's absolute magnitude using its maximum rotation velocity. With the help of the distance modulus, we can use it to obtain redshift-independent distances. In order to derive the maximum rotation velocity, we need to take additional spectra at off-center locations for our galaxies of interest.
Let me introduce the dark energy spectroscopic instrument and the current survey conducted with it. DESI is a fiber spectral curve which, due to its design, is able to take up to 5000 spectra in a single exposure spread on tiles covering about 8 square degrees on the sky. Each robotic fiber can be placed in a small petrol radius. While this design allows for a reliable instrument that can be reconfigured fast, not all fibers will always get targets, or in the case of dense regions, not all targets will get fibers, well, at least within the first pass. Several secondary targeting programs that have been approved by DESI take advantage of this fact and use spare fibers to maximize the science output of DESI. Its 5-year mission to survey 40,000 square degrees of the sky to seek new galaxies and to boldly take spectra no man has taken before. Within its first year, DESI has already observed over a quarter of its total targets. Preceding the spectroscopic survey, the photometric DESI Legacy Imaging Survey was carried out, since one needs to know where to point the fibers. This slightly wider survey provided a way to identify suitable targets for DESI. Since we are only interested in late-type galaxies that can be used for the Tully-Fisher relation, we only select galaxies with a Sursat index below 2 and with a D26 greater than 20 arcseconds, as they need to be large enough for several DESI fibers to be placed along the semi-major axis. As our goal is to measure the maximum rotation velocity, we cannot use phase-on galaxies and therefore require our galaxies to have an inclination of at least 25 degrees. Early type galaxies that will serve as targets for fundamental plane measurements are selected by having a Sursat index greater than 2.5, a maximum axis ratio, a limit in photometric redshift to remove galaxies too distant to obtain reliable peculiar motions from, as well as a series of cuts in a color-color diagram. In these cuts, we account for the issue that due to a lack of spectroscopic redshifts, we could not use K-corrected colors to identify our early type galaxies. We motivate the cuts in the color-color diagram to identify early type galaxies the following way. On the right side, we have dusty edge on these galaxies like this. On the left side, we find peculiar objects and mergers such as this. On the bottom, we have blue cloud and green valley objects that have been falsely identified with high Sursat indices.
In the case of our fundamental plane targets, we place a fiber on the center and ensure that additional observations take place during dark time in order to collect spectra with enough signal to noise to reliably derive their velocity dispersions. For our Tully-Fisher relation targets, we place fibers at a distance of 0.8 times the radius corresponding to D26 along the semi-major axis of our targets. For very large galaxies, we place additional fibers all along the semi-major axis for both the fundamental plane and Tully-Fisher relation targets for calibration purposes.
There have been several large surveys that provide data for peculiar velocities. On the southern hemisphere, there was the 6-degree field galaxy survey that had a dedicated follow-up on about 10,000 galaxies to measure their peculiar velocities using the fundamental plane. On the northern hemisphere, we have SDSS that provides about 100,000 galaxies in the DR7 footprint, for which we have derived peculiar velocities, again using a fundamental plane. Additional galaxies can be found in its extended DR18 footprint, but the inconsistent sampling makes them difficult to use for peculiar velocity studies.
We can compare the fundamental plane targets of the DESI peculiar velocity survey to all its predecessors and quickly see that we will be able to outdo them in target density and area, even for our most conservative success rate estimates. Notable all-sky programs measuring peculiar velocities via the Tully-Fisher relations are the 2-mass Tully-Fisher relation survey with a very homogeneous sample of about 2000 galaxies, and the SFI++ with about 5000 galaxies and its focus on nearby galaxy clusters.
Additionally, there is the Cosmic Flows project that aims to map the peculiar velocity field in the local universe using a combination of different methods. One of their main tools is the Tully-Fisher relation, for which they have reported an additional 10,000 measurements in 2020 for the SDSS footprint. However, the implicit modeling in the Cosmic Flows data makes it challenging to be used for cosmological tests, but it's very pretty to look at.
Now we add the cosmic flow sample to our plot. And again, the DESI peculiar velocity survey will provide more targets than all the previous surveys combined. We use the results from the survey validation to estimate the success rate of our target selection given the overall DESI targeting algorithm. In the spectroscopic data collected by DESI before summer 2021, we got observations for almost 30,000 of our fundamental plane targets. After applying additional color, redshift and H-alpha cuts to remove misidentifications, we keep about 20,500 galaxies. For 16,000 of these galaxies, we have spectra with sufficient quality to measure the velocity dispersion with less than 10% uncertainty, and this in spite of a minor bug in the early target selection giving us fewer high-quality spectra. The early observations of the Tully-Fisher relation are proceeding much slower because we need multiple passes to get the required data. However, during the last stage of survey validation, the 1% survey, we were able to obtain 1,600 measurements. Since the details of our fiber placements and targeting were very different during survey validations, we are currently working on the year 1 data of DESI and better cleaning methods for sample to provide more solid numbers of our success rates. But based on our current estimates, we expect up to 200,000 successful observations of the fundamental plane galaxies and up to 60,000 observations of Tully-Fisher relation galaxies within the current spectroscopic footprint of DESI. Since after all, DESI is primarily a cosmological experiment, we need to be able to do something more than just some fancy plots with our peculiar velocity survey. Carl and Howlett used a pessimistic estimate of only our fundamental plane targets to estimate the improvement in the f-sigma-8 measurements for low redshift DESI targets. We found that at these ranges, we can tighten the constraints on the growth rate f-sigma-8 by more than 30%. Thanks to the DESI peculiar velocity survey, we'll be able to significantly improve the constraints from the DESI Bright Galaxy survey for the evolution and scale dependence of f-sigma-8. Thanks to its high target density and large sky coverage, the DESI peculiar velocity survey will be a driving force for cosmological measurements in the local universe for years to come.
I'm looking forward to answering your questions either in the Slack channel or during the live discussion session. Also stay tuned for upcoming paper on the target selection of the DESI peculiar velocity survey. If you want to support my work by hiring me, I will be on the job market this fall looking for a new postdoc position starting next summer.